Hello everyone. My name is SHIV VISHWAKARMA. My topic is design of ultra wideband MIMO antenna for indoor wireless application. We have done this research under the guidance of Mr. Mohammed Sibli sir, and my teammates are Vipin, Sunil, and Turvasu. Head table of contents from which there are introduction, motivation, objective, abstract, literature review, system design, result and discussion, and lastly there is conclusion. If we talk about introduction about ultra-wide MIMO band, ultra-wideband MIMO antenna, an antenna is a transmitter between a guide wave propagating in a transmission line and an electromagnetic wave propagating in an unbounded medium like air. It is an antenna technology that is used both in transmission and receiver equipment for wireless radio communication. Ultra-wideband is defined as a system having bandwidth greater than 5 megahertz. An ultra-wide system can make use of huge frequency bands from between 3.1 to 10.6 gigahertz in regulation imposed by the Federal Communication in the United States and other European Commission document in Europe. The permitted power spectral density of the ultra-wideband signal is rather limited. The channel capacity of ultra-wideband system is proportional to the number of transmit and receive antenna. Data rate can be significantly increased further by combining ultra-wideband and MIMO. This region is the same as the one that triggered the research era on MIMO about 2 decades ago. Even if lower data rates are in focus, the trade-off between bandwidth and the number of antennas could facilitate the antenna and amplifier design, which is still a challenge for ultra-wideband systems. For example, the bandwidth requirement could be almost reduced by half if 2 antennas instead of 1 antenna on the both transmitter and receiver sides are deployed. Next, we come to motivation. We got motivation in this project that MIMO system has a higher data rate and higher reliability with extra power and bandwidth. MIMO antenna increases the antenna gain and extend the coverage of the system. The ultra-wideband technology is assigned a bandwidth from 3.1 to 10.6 gigahertz. The ultra-wideband technology is leveled for multi-gigabytes wireless communication. Objective of this project is to design ultra-wideband MIMO antenna for indoor wireless application. To present a brief survey on ultra-wideband antenna technology and to discuss and analyze its performance and development and its benefit using MIMO system for ultra-wideband communication. Next, we come to abstract. Here, an ultra-wideband technology combined with multiple transmit and receive antennas is a viable way to achieve data rates of more than 1 gigabytes per second for wireless communication. Ultra-wideband is typically applied to short range and therefore mainly indoor communication in environments characterized usually by dense multi-part program. Now, for this type of environment, multiple input, multiple output system allow for a substantial increase of spectral efficiency by exploiting the inherent array gain and spatial multiplexing gain of the system. We have used a tool called CST, computer simulation technology, which is high performance 3D electromagnetic analysis software package for designing, analyzing, and optimizing electromagnetic components and systems, which we used for making this project. Here are our some literature reviews from which we find there are some findings and shortcomings of the recently presented papers on different mainly on IEEE journals. Hence, there are likely 20 literature surveys we have done, from which we have proposed antenna. So here our system design. We have designed a system like we have a small dimension in this project. We have proposed the dimension parameters value are the width of the antenna is 18.0 length of the antenna is 36 mm, and radius of the circular patch used in this antenna is 4 mm, and the side width of the antenna from circular to bottom of the radiating element is 5.6 mm, and length of the side radiating element to this stub is 7.81 mm. Here are the brief dimension discussion about this antenna. We come to system design. The proposed antenna architecture is inscribed on the other side of the substrate and comprises of the ground planes. It's difficult to achieve this physical antenna structure in a MIMO antenna architecture for ultra-wideband implementation while balancing low reciprocal coupling between individual antennas, because MIMO covers a wide range of ultra-wideband applications. Keeping the decoupling element in the MIMO antenna is problematic. The antenna has an omnidirectional radiation pattern and the estimated envelope correlation coefficient, which is less than 0.04 nearly or 0.05. In addition, the MIMO arrangement requires no isolation or matching circuits, making it more compact and suited for USB dongle applications. The dielectric material we use in this is copper, which is annealed, and a substrate is called WRFER-forum, which is a lossy in character, with a dielectric constant of 3.8 and a loss strength of 0.009. For the ultra-wideband implementation, the dielectric material has a thickness of 1.575 mm. The antenna dimensions are 36 in 10 mm square with a tangent loss of 0.009. The proposed antenna architecture is inscribed on the others which we discussed. Here we come to a result and analysis. We know how the antenna is performing by its parameter. It's called S parameter. The S parameter is the input-output relationship between ports or terminals in an electrical system described by S parameter. For example, if we have two ports, namely port 1, port 2, S12 symbolize the power transfer from port 2 to port 1. The power transported from port 1 to port 2 is represented by S21. In a multi-port network, SNM represents the power transferred from the port M to port N. A port can be roughly described as any location where voltage and current can be delivered. The radio terminals, which give electricity to the two elements, could be the two ports of a communication system with two radios, which can be radio 1 and radio 2. Here are the S parameter simulation, which describe we have a perfect impedance which is lower than -10 dB, which is good for ultra-wideband MIMO design. Here are the some parameters like S11, S22, and S12, S21, which is part of S parameter, in which we can see different results. Here another result which is important for ultra-wideband MIMO antenna design, which is diversity gain. Diversity gain is the mixing antenna element that experience different levels of fading, in which diversity techniques are utilized to lessen the influence of fading. The number of independently fading antenna elements can be used to measure diversity performance. In figure 7, we can see diversity gain curve. This shows gain is quite high at 9.95 dB from 3.7 gigahertz to 4 gigahertz, and almost 10 dB from 3.1 gigahertz to 10.6 gigahertz. And another result is ECC, which is called envelope correlation coefficient. Under ideal conditions, the two-port MIMO correlation coefficient should be less than 0.05 or 0.04. The ECC is less than 0.05 in this throughout the frequency we provided, which is within the operational frequency in ultra-wideband MIMO system. Another result is surface current density. We'll look at the surface current distribution of the MIMO antenna to better understand the isolation between two ports. In figure 9, we can see the surface current distribution at 21 gigahertz. And next is radiation pattern of antenna. Radiation pattern of an antenna represent the energy it emits. Radiation patterns are diagram that show how radiating energy is distributed in space as a function of direction. The energy being emitted is reflected in the pattern made in a given direction. The arrows indicate the directions of radiation. Here, far field gain at phi is equal to 0, and far field gain at phi is equal to 90. At a frequency of 24.8 gigahertz, and another is a frequency of 26.7 gigahertz, which is also in degree of phi is equal to 0 and phi is equal to 90. Yeah, phi is equal to 90. Okay. Next, we conclude this. This presents the ultra-wideband MIMO antenna for indoor wireless system with a small dimensions of 18 into 36 mm square. From 3.1 to 3.1 gigahertz to 10.6 gigahertz, the antenna's S11 is less than -10 dB. According to the simulator, the antenna offer a low ECC of less than 0.05 decibel and a variable block gain. The MIMO directional antenna primary characteristics give it a viable candidate for ultra-wideband as well as super wideband purpose, because we have such simulation like S parameter showing it up to 25 gigahertz is performing well, so that it's well good for our research. And lastly, thank you from my side. That's it.
Thank you for your wonderful presentation.